Say you have a waveguide and you solve Maxwell's equations to find the eigenmode of that waveguide. And you find an eigenmode with a certain propagation constant beta and some electrical and magnetic field profiles. Can you then also show that the following set of parameters also corresponds to a solution of Maxwell's equations? And because you have a minus sign here for the propagation constant, you can associate that set of parameters with a backward propagating eigenmode. So pause the video, expand Maxwell's curl equations into the different components, and see if you can show that if you have a solution like this, then automatically these sign changes will also result in a solution. So Maxwell's curl equations. So first of all, we have the curl of the electric field. The curl of the electric field is minus j omega mu the magnetic field. And then we curl the magnetic field to give us j omega epsilon e. Quick recap for the curl, how we calculate the curl. So we construct a determinant, and then as first row, we have the unit vectors along x, y, and z. Second row is the partial derivative. So partial derivative with respect to x, partial derivative with respect to y. But then for the partial derivative with respect to z, since we're looking for eigenmodes, which have a z dependence of exponential minus j eta z, if we take the z derivative, that just corresponds to a multiplication with minus j beta here. Good, and then we have our components of our vector field, ax, ay, and az, where here a and b a can stand for either e or h. Now, if we then expand this into the different components, so first of all, for the z component, or the x component rather, we pretend that these lines and these columns aren't there, and we calculate the subdeterminant here. So that gives us the partial derivative of az with respect to y minus j beta ay for the x component. For the y component, we have minus the partial derivative of az with respect to x. And then we have minus j beta ax for the y component. And then finally for the z component, let's have a look. We have partial derivative of ay with respect to x minus partial derivative of ax with respect to y for the z component. Okay, so now we know the general pattern of the curl. Let's just substitute that here and write down 6 equations for the 6 components of these guys here. So pause the video and do that. Okay, not difficult, but just slightly painful to do here. So the first thing we're going to write down is the curl of the electric field up there. If I can get it in view. So the curl of the electric field minus j omega mu, the magnetic field. So the first component is going to be the x component. So that's the partial derivative of ez with respect to y minus j beta e y. And that's equal to minus j omega mu, the x component of the magnetic field. Moving on, minus partial derivative of ez dx minus j beta ex equal to minus j omega mu h y. And then finally, partial derivative of e y with respect to x minus partial derivative e x with respect to y minus j omega mu h z. Good. Next step is do the same thing for the magnetic field, which has a very similar structure on the left-hand side, and then some minor changes on the right-hand side. So let's just do that. So we have the partial derivative hz with respect to y minus j beta hy equal to j omega epsilon ex. Okay, two more to go. Minus partial derivative hz with respect to x minus j beta hx j omega epsilon ey. And then the final equation at long last is the partial derivative of hy with respect to x minus the partial derivative of hx with respect to y equal to j omega epsilon ez. And now let's see what happens if we do these sign changes. So say we find a solution to these equations. So we have a solution given by, let's go back here, given by this combination of parameters here. So we have a z component for the electric field and a transverse component, which is an xy component also for the electric field, similar for the magnetic field. And then also we have a beta, a propagation constant that we find. Let's see what happens if we flip the sign of our propagation constant, if we flip the sign of the transverse, i.e. the x and y component of h, and if we flip also the sign of the z component of E. Hopefully we come to this conclusion that that also is a solution, so that nothing changes if we make these sign changes. So the first thing we should flip is the z component of the electric fields, which we find here, here, and then also there. Okay. Next up, flipping the x components of the magnetic fields. So we find one over here. We also find one over there. And we find one over here, because this should be an x, of course. So you find one over here. Y component of the magnetic fields, so which makes an appearance here, then also there, and obviously there. Final thing we need to do is flip the sign of our propagation constant, which we find here, 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 and here. Okay, now we've identified which signs we should flip, and then if we have a look at the first equation, basically means that we should just flip the sign of all the terms in the equation. So nothing will change. So that's fine. That means that if our forward set is a solution, then our backward set will also be a solution. Same thing for here. We flip signs, but we just flip the signs on all of the terms. So nothing happens. Nothing happens in the third equation. Same for these equations, because we have two sign flips, but they occur in the same term. So nothing changes here. And then finally also nothing changes there. So we have indeed shown that if we have a solution given by these guys here, then by making these sign flips, we automatically have another solution. And because we have a minus sign here for the propagation constant, that corresponds to a backward propagating mode.